right, so we have here Chapter 4, Problem 70, and we're told that we've got a 75 kilogram person standing on a scale, and they're in an elevator, and we're tasked with figuring out what does the scale read in newtons and in kilograms under various conditions. So let's go ahead and draw the picture. We've got our happy experimenter here standing on the scale inside of an elevator. And the scale will indicate some reading. Okay. So what we need to do is figure out what the reading will be under several different situations. What we're probably also going to want to do is add on to this diagram a free body diagram. I say that because, well, when we talk about conceptually, the concepts that we'll have here, we know from experience, and we can recap this, that the scale actually reads out what the normal force is acting on the person. That actually comes from Newton's third law, because whatever force is pressing up on the feet of the person's feet is pressing back down with the same force, same magnitude, but opposite direction. So in that case, the force pressing up, that's the normal force, and so we know the scale is reading that out. So you can write down that we're going to use Newton's third law, and of course we'll have Newton's second law in this, as we almost always do. Newton's second law, Newton's third law. And when we're using Newton's second law, we oftentimes want to use a so-called free body diagram. So let's draw the simple thing of the person with a particular mass. We know that there's a force of gravity always pointing down that has a magnitude of mg. And there's a normal force which is pressing up, not always up, but it's going up in this direction because that's the direction that the normal points. Normal force. And most generally, Newton's second law tells you the equation that we'll want is F net equals to ma. It's a vector equation. We only need to worry about the y direction. We have the net force of what's up, normal, minus what's down, that's the force of gravity, or mg, and that's equal to the mass of the person times the acceleration. It's the acceleration in the y direction. I'll go ahead and write it that way. So we can simplify this and use our master equations for the whole problem, take this mg to the other side and just factor out an m to make it look prettier. This is ay plus g, in parentheses, times the mass, and that's the master equation that we're going to use for parts A through E. Okay, so let's realize something. In parts A, B, and C, the acceleration is actually 0, and this is sort of a trick question. The elevator being at rest, the elevator climbing at a constant speed of whatever, or going down at a constant speed or whatever, constant speed, and we know it's one direction, so it's actually constant velocity. A through C has constant velocity, which implies acceleration equals 0. Which means this term is 0. In other words, the normal force, or what the scale reads, is just equal to m times g. Okay, I forgot to indicate here the things that are known, but you probably picked up on the mass of the person is 75 kilograms, and g is 9.8 meters per second squared. Okay. So for parts A through C, we know that the normal force, based on this argument, is mg, which is 735 newtons. All parts, 735 newtons. You can convert that into kilograms if you want by taking the normal force dividing by g, and that just gives you back the mass of the person. That's sort of what you'd expect, right? The scale is designed to determine, it determines mass for you when you're on Earth and not accelerating. So we could say that this is 75.0 kilograms, if you like. The slightly tricky parts come in part D and E. In part D, we're told that the elevator is accelerating upward at 3.0 meters per second squared. Before we do any calculations, hopefully you can use your intuition to remember what it's like when you get in an elevator and it starts accelerating upward, and what it feels like on your feet. You know that you have to kind of work a little bit harder to keep yourself from falling over. That should tell you that if you're working harder to go up, that means the scale should be reading a higher number. That's consistent with the fact that the acceleration here is positive. In other words, it makes g effectively bigger. That's one way to say it. The normal force here is therefore the mass of the person. The acceleration in this part of the problem is 3.0 meters per second squared plus g of 9.8 meters per second squared. The mass of 75 kilograms gives you a number that is about 960 newtons. Okay, 960 newtons. If you then divide this by g, that's the way that you might have a scale set up to compute your apparent mass. This would give you a number that's quite large, about 97 kilograms. In other words, you would feel like you were 97 kilograms if the elevator was accelerating upward. Finally, part E, you expect something similar but going in the opposite direction. If you're accelerating downward at 3 meters per second squared, the acceleration is negative. So here, the normal force is the mass m times a minus 3.0 meters per second squared plus 9.8. It effectively makes this term smaller, and what you find out is that this force is 510 newtons, and that would give you an apparent mass. It would feel like you only weighed 52.0 kilograms.